My name is Nguyen, and my teammates are Phuong Tran and Dharmang Solanki, and today we'll be presenting the centralized information system for electrical management. So, a little introduction. As you know, PG&E has been shutting down power recently in response to the global warming threat that we're facing. So, they're turning off power to prevent wildfire and helping to keep communities safe, because as you know, in 2017 PG&E electrical current overload in their conductor causes one of California's deadliest fire. So what we're going to do today is present to you a way that uses IoT to help conserve power and to prevent equipment from overloading, right? So currently, as you know, power conservation are done through warnings, like the governor or PG&E send out warnings telling everyone to conserve power, but there's no way of really enforcing it. So with our IoT thermostat, we can effectively enforce conservation during times where conservation needs to happen, right? Especially during peak fire season during the summertime, as well as really dry winter season, thunderstorm season, for example. So this IoT thermostat will reduce the need for an outage, obviously. And even if an outage does happen, it can be done with little to no impact. So let's get back to our presentation. So this is our table of content. So we have a problem statement and how we're going to solve it using IoT, our technology stack, our architecture diagram, and then how we'll split the work, and then the MongoDB schema, and then a demo. So Phuong will do the front end, the UX design and QA, and then Dharmang will do the hardware and then cloud deployment, and then Nguyen will do the data and middleware. So let's get back to our problem statement, right? So global warming causes fire usually around June, July, and August time. So PG&E usually just cut power where fire most likely to happen, without regards to anyone. So usually elderly or young children, they need power for example, their medical devices. Children cannot, fare well in really hot weather, and so is the elderly. So we can use our IoT device to basically reduce the need for rolling blackout through conservation. And then even if there is a need for the blackout to happen, we can do it very quickly and then restore power to those who need it first. So how we're gonna do this using IoT? So we record the temperature of each house and apartment using our device. We send that data to the cloud, and then we calculate the average temperature of each house and apartment unit, and then that will then turn into our visualization to effectively planning on how to cut electricity. And then this is our technology stack. So we have 3x of the DHT11 temperature sensor. They're cheap but very accurate, so they have a plus or minus 2 degrees differences each time. And then for the devices, we used a Raspberry Pi to basically act as a thermostat. And then for the database that we'll be storing these data, we pick MongoDB because of its unstructured. It's able to take unstructured data. For example, like temperature is very unstructured data. And then for our cloud platform, we pick AWS. And then lastly, for our web app and visualization, we pick ClickSense. So this is our architecture diagram. You have here apartments, or you have an individual house. They each have a Raspberry Pi with the DHT11 sensor. and these sensor will then send data back to the cloud. So there's a couple of preface. There's two things that we are working on to basically have these devices still up and running despite a blackout. First is a non-explosive battery pack that can be attached to these devices that we're looking at 2 to 3 days of use that is rechargeable also. So once the power comes back on, the Raspberry Pi will start charging back the battery pack. And then the second thing is satellite internet. So because when there's a blackout, usually the internet provider power will also get shut off. So we're looking into satellite internet. So right now there's SpaceX that kind of offers satellite internet, but there's not much options that we're choose from. So in the future there will be a lot of options, but so far only SpaceX is offering satellite internet. So this is our MongoDB schema. As you can see, we have these to keep track of the temperature. So the average temperature here belongs to this house, and then with the coordinate, so the coordinates here are geolocation coordinates, so they're longitude and latitude. And then for our cloud deployment platform, we experiment with a standalone MongoDB as well as a cluster of MongoDB, and we found that the cluster performed much better, obviously because it separate each task. So a standalone MongoDB cluster acts as both a config, a router, as well as the server that hosts the record. Whereas if you have a cluster of MongoDB, they all have different roles. So you have a MongoDB router and configuration, and then you have a MongoDB shard server, and shard server. So these shard server acts as buckets. So if you configure your sharding scheme to be correct, if you insert 36 record, each one of these server will have 12 records inserted to them. So this is done to be more resilient and fault tolerant. And then let's go to the Raspberry Pi demo. So I have here a VNC viewer, which is basically a remote desktop into the Raspberry Pi, and then I log into my Raspberry Pi. So in here I have a couple of classes in my Raspberry Pi code. So we use singleton pattern, which is an object oriented pattern, which basically separate each object into each own class. So you have a house object, an address object, a connect to MongoDB object, and then you have a local thermostat object, and then you have a main the main class to run all these objects. So for this demo, we'll be demoing the home class, the config, where we keep our configuration, and our geolocation class, which basically take in an address and translate it into longitude and latitude. So let's look at how we can run this. So the main class builds a home object. So once the home object is built using config.address and config.device ID, it then sends that temperature, it then sends that object into the thermostat object, and then returns back the temperature, as you can see here. The config.py acts as our configuration file. That way we do not have to edit the code if we were to set up multiple devices. So for example, for this demo, I put I live here, and this is my city, my zip code, my state, and then this address name is just something to keep track of. So we do not use this, but this acts as a identifier for whoever is looking at this file to know that this is my address. We're not doing anything with this home ID for now. And then this device ID is a unique number that we use. And then this is our AWS MongoDB, and this is our port number. So to run this, I would do and we'll get the temperature back. And then it will send to AWS this record. And then for our visualization, we pick ClickSense to be our visualization tool. So ClickSense is a cloud in-memory visualization. So we picked this because it's very easy to get started. So you can get a free trial to get started, but then you subscribe yearly. So usually it's like $200-300 yearly just to get a tenant. And then once you get your tenant, you can build visualization tools on top of that on your database. So this is what we have as our visualization. So with this visualization, you can do a lot of things with our backend. So for example, the first page is device summary. As you know, each device has a unique device ID, so you can keep track of that device ID. You can keep track of my device ID. So as you know, it sends data on these days. And then you can see its average temperature went from 21 all the way to 25, right? So you can also filter by zip code and see all the devices. So let's filter by 90021. And then once you filter that, it will keep all of that into the next page also. So this is the device daily report, which basically report back all the devices as well as the max temperature, the average temperature, and the min temperature. So as you can see, the max temperature, the average temperature, and the min temperature for the zip code 90021 is about 32 degrees max, 25 degrees average, and 17 degrees minimum. They're all in Celsius, right? So if you unzip this, you'll see the average temperature changes, but the max and the min remains the same. And then the next one is this is something that we've been working on. So this thing is not as accurate as I would like to be because of the open source tools that we're using. So most of the tools we're using are free. However, what we try to do is map the device to its correspondent area, right? So you can see here some of these are incorrect. For example, 90021 should not be in Long Beach or nearby Torrance, right? It actually should be here near downtown LA, right? So if you look up this is where the 90021 zip code will be, and this is where we map most of our devices, which is correct. So there's a couple of ways that you can make this more accurate. First of all, we would need to use a better geolocation mapping tools. So like I showed before, our geo mapping tools are we use this open source map tools called OpenStreetMap. However, if you want, you can pay Google subscribe to Google Map API, and it will get a much better accuracy, for example. And then and then if you want to look at your specific device and where it's located, you can look at mine, for example, and see where this single device is located. So this is located here, and you can zoom out and zoom in depending on your needs. So that's conclude the demo. Thank you.